Alright, so in this lecture, we are going to look at some of the past questions. Now, we have the 2023 past question, which is a recent past question, which says, the first question we have here is, draw the structure of testosterone, indicating the part of the molecule that is susceptible to oxidation and ways to prevent this effect using a synthetic scheme. Now, look at it. What is the structure of testosterone? Now, first of all, you have to establish which of the steroid or which of the steroidal nucleus this testosterone fall into. And you will agree with me that testosterone is what? An androsten. I've said this before, right? Androsten. And from the name I gave, the acronym I gave earlier, I said go what? East and play cholesterol, right? Or cholesterol. Now this is 17 carbon, this is what? 18, this is 19. So testosterone is 19. That's 19 carbon. So what do? You draw the structure for 19 carbons. So first of all, you know the steroidal nucleus will be something like this. Then you have this group on top, and then of course you have this 5-membered ring here, right? Now, according to what we know that we are going to have something like CH3 at this position, right? And then here you're also going to have what? CH3. Is that okay? Now for testosterone, you are going to have an OH as a substituent in position number 17. Is that okay? And then this group here, you are going to have a double bond. And here, you're also going to have a double bond. So testosterone is, if you want to count, this is 1, this is 2, this is 3, this is 4, this is 5. You can see that it has this alpha beta unsaturated ring, right? Now, one thing that you should also know is most times they usually indicate this alpha beta unsaturated ring with delta, which is this symbol here. So when it's something like delta 4, what does it tell you? It tells you that at position number 4 you have what? A double bond. Now, the next question, this is the structure of testosterone. So you are going to come here and say testosterone. Is that okay? Now, they say indicate the part of the molecule susceptible to metabolism. Now, the part of the molecule that is susceptible to metabolism in this structure is this group here. This OH group here, susceptible to metabolism. It can be oxidized. Is that okay? To what? It can be oxidized to ketones. And oxidation to ketone reduce the activity. Is that fine? Oxidation to ketone reduce the what? Activity. So most time it's better is in that form. So that is the part of the molecule that is susceptible to what? Metabolism. And then the way to prevent this using a synthetic scheme. Now when you talk about synthetic scheme, I don't think they actually want you to draw the mechanism of reaction. What they just want you to do is, how do you think they can actually prevent this using a synthetic scheme? Generally, that is the meaning of this question. So how do you think they can prevent this using a synthetic scheme? Is by methylating this position. Are you getting it? By adding methyl group to position number 7. So you can say this can be prevented by methylation of what? Position number 7. Position number 17. So it's going to now give us what? Methyl testosterone. So instead of us having this structure, we may not be having something like this. So methyl testosterone. You can decide to draw this structure of testosterone and then just put methylation to indicate how you can actually prevent that, instead of writing the mechanism of reaction. So you have methyl testosterone. That is the structure I'm trying to bring out. Now the structure of methyl testosterone is testosterone with OH, and then you have a methyl group still at position number what? 17. This is the structure of methyl testosterone. Methyl testosterone is more stable than testosterone. Is that okay? Methyl testosterone is more stable than testosterone. So that is the way you can actually solve this particular question. It's a very simple question. Is that okay? Now, the next one. Outline the synthesis of sibesteroid using p-methoxybenzaldehyde. Now, first of all, you have to note what you have here. What do you have here? P-methoxybenzaldehyde. So what is the structure of p-methoxybenzaldehyde? P-methoxybenzaldehyde is at position number, at P, you have methyl group, and then you have a benzaldehyde. Benzaldehyde is a structure that looks like this. All right? C double bond H, and then OCH3. This is p-methoxybenzaldehyde. Now, you will actually need 2 molecules for this reaction. You will actually need 2 molecules of p-methoxybenzaldehyde. Is that fine? Now, you react this with KCN. Can you still remember the synthesis of benzoin from benzaldehyde, where you use KCN? Now, what will happen is a beta hydroxy ketone will be formed, but then you need 2 molecules of this p-methoxybenzaldehyde in order to form the beta hydroxy ketone of aromatic nature. So this is going to give us CH3. Then you have the oxygen, and then this benzene ring I'm trying to draw here. Don't mind the structure. Here you are going to have OH. This hydrogen will come down. This hydrogen will come down, and then you attach another molecule of what? Of this structure here. So you are going to have C. Here become double bond O. Remove the hydrogen from here. The mechanism of reaction, I don't think it's something you want to learn. And then you have something like this. This is another molecule of p-hydroxybenzaldehyde. So this structure here is a combination of 2 molecules of p-methoxybenzaldehyde joined together. Now, this, first of all, when you are actually drawing structures like this, the first thing that you should have at the back of your mind is the structure you intend to draw, or the structure you intend to synthesize. What do you intend to synthesize? Sibesteroid. What is the structure of sibesteroid? Because that is like a guiding principle that will help you to actually draw the right thing. Now, what is the structure of sibesteroid? Sibesteroid is something like this. You have C double bond. Now, most time the trans sibesteroid is more stable than the cis sibesteroid. Is that okay? And then you have at this position you have C2H5. Is that okay? At this position you have what? C2H5. Then what other thing do you think you have in the structure of sibesteroid? You have the normal benzaldehyde, benzene nucleus attached, which is something like this, with what? OH. Space here is not enough. This benzene ring, please. You have double bond, and what? OH. This is the structure you actually intend to what? To synthesize. That is the sibesteroid. Is that okay? Now, how do we achieve this? It's very easy. So it means you'll be adding this alkene group, or alkane group rather, to each of these positions. That means you add alkane group to here, you add alkyl group here, you add alkyl group here. Now, how do you actually add the alkyl group? Is by reaction with Grignard reagent, followed by hydrolysis. So if you react this with Grignard reagent, followed by hydrolysis, now the Grignard reagent will carry the number of carbons that you need here. So in this case, it will carry C2H5. Now, what will happen is that the Grignard reagent, the C2H5, which is negatively charged from the Grignard reagent, will actually come and attack this position here, and then this one will come up. So that at the end of the day, the product of this reaction will be something like CH3O, and then you are going to have something like this. Then you are going to have COH. Here will be H. Here will be C2H5. Because I told you that the C2H5 will come here. This group here will be, when this one pack here, be O minus. But upon hydrolysis, it's going to give us what? OH. And then you have this group here closed. Again, this benzene ring, then OCH3. Is that okay? Now the next step is dehydration. You remove water. So if you remove water from this structure, now you remove the water in such a way that you remove hydrogen from here, a double bond will be formed here, and then remove the oxygen from here. So that at the end of the day, this is what you are now going to have. CH3O, right? And then you are going to have this. Remove hydrogen from here, remove hydrogen from here. Whenever I remove hydrogen from two hydrogen from the same carbon, a double bond will be formed. So a double bond will be formed here. And then you are going to have C. Remove oxygen from here. What are you getting? Because 2 hydrogen plus 1 oxygen will be water molecule that you remove. So here will be what? H. And here will be what? C2H5. And then you have your benzene ring again, OCH3. Is that okay? Now, the next step is this reaction, you are going to treat it again with another Grignard reagent. Is that okay? So the Grignard reagent you are still going to treat it with will be what? C2H5 MgBr. So what do you think this is going to give? Going to give us CH3, CH3O. Alright, and then you have something like this. Then you have what? OH. Because I told you that whenever you treat something with Grignard reagent, the C2H5 part of the Grignard reagent will actually come here, attack here. Then this will what? Go up. So you are going to hydrolyze this. That is why you are going to have acid hydrolysis too as part of this stuff you have here. So that at the end of the day, you are now going to have this C2H5 attached to this position. You can see it here, attached here. So you have C2H5. Then you are going to have here C. Here's what? H. Here's another C2H5. And then you have, yes, OH. Alright? Now, at this point in time, the next step you are going to take is to dehydrate. Now, when we talk about dehydration, what does it mean? Removal of what? Water. You can remove OH from here, remove hydrogen from here. What will be formed here? A double bond. So, at the end of the day, the product now will be, let me erase any one of these from here. So that at the end of the day, the product to this reaction, to dehydrate means to remove water. Dehydrate and demethylate at once. That means remove water and then also remove what? CH3 group. Dehydration plus demethylation. Now, if you dehydrate plus demethylate, of course this is still OCH3 here. if you dehydrate plus demethylate, it means this CH3 will be replaced with what? Hydrogen, hydrogen. So here you are going to have OH, and then you have your benzene ring. Then here will be C, double bond C. Alright? Here you have C2H5. Here you also have what? C2H5. And then here you have your benzene ring, which is something like this. And then you have OH. Now, this form, the way it is the cis form. This is the best error. But this is inactive. The active form is a trans. So in order for us to achieve trans, all what I just need to do is remove this one from here and place it at this position, which is C2H5. So this is trans stibesterol. Stiboesterol. And this is how to actually synthesize it from p-methoxybenzaldehyde. Now if you check your material, you are going to see it under anisine synthesis. Is that okay? Like benzoin, formaldehyde, 2-benzaldehyde, you call it benzoin. Then, but this one will be methoxybenzaldehyde, you call it what? Anisine. Alright? So that is that for this question. Now, the next question is discuss the SARO of progestins. Discuss the SARO of progestin. Now, before you can discuss the SARO of progestin, you must be able to draw the structure of progestins. Now, what is the structure of progestin? Progestin, which of the carbon chains do they have? They are pregnane, right? Right? Progestins are pregnane. Now, if they are pregnane, what does that mean? It means they are having, say, go east and play 21 carbons, right? So, first of all, we have to draw the nucleus with 21 carbon. So, you have to draw the structure of the progestogens. Now, you should know one thing. This is very, very important. Now, the progestogens, they have different classes. You have the natural progesterone, progestogens. Are you getting it now? Progestins. The natural progestins. Example is the progesterone. Are you getting it? You have the 19-nor derivative. And then you also have the testosterone derivative. That means those ones that we are gotten from testosterone. Are you getting it? Now, how do we solve this one? How do we provide solution to this? Say discuss SARO of progestin. You cannot discuss SARO until you must have drawn a structure to illustrate what you are actually talking about. So let's draw the structure of progestogen. Progestins, progestins. Progestin. The activity is called progestational activity. That is what is just in my mind. So you have this as the benzene ring. Alright. This is the structure of, this is the normal distance. Of course, you know you have CH3 here, right? Then here, what do you have here? CH3. This structure is not big enough. I need a very big structure that I can. So let's draw the structure. I needed something that was at least a little bit bigger. So we have, let me just use this to try and bring out the structure of. So we have something like this. We'll have another benzene ring. Alright. Then you have another benzene ring at this position. We will have to turn this one. Is that okay? And then we now have 5-membered ring. Can do it like this. Is that okay? Now, if you look at all these other positions, there are substituents. I told you here there's a substituent. Here there's a what? Substituent. Now, one thing you should also know is for the progestins, there will be a double bond here. Is that okay? And there will also be a double bond here. But this double bond now will carry what? Oxygen. Here, CH3. Here, CH3. But the number of carbons are not complete. Because if you count, this is 17 plus this to 19. Now, for the progestins, they usually have CO, then CH3. COCH3. This is the typical example. Typical example, progesterone. This is the structure of progesterone. Is that okay? This is structure of progesterone. If you want to number, here's number 1, here's number 2, here's 3, here's 4, here's 5, here's 6, here's 7, here's 8, here's 9, here's 10, here is what? 11, 12, 13, 14, 15. I think we jump 1. Show of them. This is 9, 10, 11, 12. Oh, we jumped 1. Here is what? 13. Here is 14. Here is 15. Here is 16. Here is 17. So you see that at position number 17 has a ketone group. That is why they call them what? Progesterone. Sometimes you may want to put it this way to indicate the ketone group. Are you getting it now? So if I want to count now, if here is 17, now listen, here is always what? 18. Here is what? 19. Here will be 20. Here will be what? 21. And of course, we know that progesterone or the progestins, they have how many carbons? 21 carbons. You must note that whenever we talk about progesterone or the progestins, they have this C-double bond O. Are you getting it now? So when we are talking about the structural activity relationship, we are talking about things like, what are we going to do to number 17 that may increase the reactivity, biological activity, the stability? What are we going to do to this bond here? Because normally this bond is not part of the nucleus. Are you getting it now? So what we are actually looking at is, aside from the general nucleus, the nucleus is the pregnant nucleus, right? Apart from the pregnant nucleus, what do you think we can actually do to this to enhance the biological activity, or maybe increase it, or what? Reduce it. That is the structural activity relationship. So if you are talking about structural activity relationship, it means we must talk about number 3 here, right? It means we also talk about what? Number 4. Are you getting it? It also means we talk about this what? Number 17 here. Are you getting it? It's very, very important. Maybe some other substituent. Now, talking about the structural activity relationship, there is important thing. Say, some progestational activity. For some progestational activity, only one oxygen function needs to be present as a 17 beta methyl ketone or a 17 OH with 17 alpha side chain, e.g. etesterone. Now, what do we mean by this statement? Listen. What we mean is, sometimes we only need one beta hydroxy group, or what? Beta ketone for the progestational activity. That means to carry out the general activity of this class. So it means this one here that usually have this double bond here is okay. Are you getting it? Now, also, if this substituent here should be what? Should be beta. You know what beta and alpha is now? Alpha is the one that usually use the what is it called? Dotted line. So it means if I want to put any other substituent apart from this group here, what am I going to put there? Dotted line. Example they gave to us here is what? Etesterone. Now, what is etesterone? is very, very easy. Ethylsterone is when you add ethylene group to this position, as opposed to this group here. What you now have there is what? Ethylene. It's called ethylsterone. Now, alright, so let's look at the structural activity relationship. The first thing you have here, say for some progestational activity, only one oxygen function needs to be present as a 17 beta. That means at the 17th position, you only need to have only one oxygen functional group. It can either be 17 beta methylketone or 17 beta hydroxy with a 17 alpha side chain, e.g. ethylsterone. Now, what is the structure of ethylsterone? Ethylsterone has the following structure. Let's try and draw the structure of ethylsterone based on everything we've learned so far. So you have something like this. You have another ring attached. Alright. Have another ring. This one is attached here. And then finally, you have a 5-membered ring. Alright, good. Now what you are trying to say here is very easy. For ethylsterone, this is the structure of ethylsterone. You have C here. Every other still remains the same. Now, do you know the only difference? The only difference is you have O here. Now for ethylsterone, you also have this group here. Alright? And then you also have this group here. Now, the only difference in ethylsterone is instead of us having a straight or this methylketone, this is the structure of methylketone, right? Instead of us having methylketone, what we'll have is an ethylene group added at this position number 7, but it's alpha to it. So you have something like this. This ethylene group is alpha, and then you have a hydroxy group that is what? Beta, which is OH. So what they are just trying to tell you is that for this thing to be potent, at position number 7, is either you have a methylketone that is beta, that is a beta methylketone, or you have a beta hydroxy group present there. And the next substituent that will be attached should be alpha. Is that okay? So that's just the general idea in the first thing under the structural activity relationship. Now, they usually possess a 4-in-3 own structure, and conversion from 4 to 5 destroy progestational activity. I told you earlier when we started that some of the things that we will look out for are this bond here, this bond here, this bond here, right? We've talked about this bond, that this bond can either be a beta methyl ketone or what? A beta hydroxy group. Is that okay? Now, why the substituent present should be what? Alpha to it, e.g. the structure of what? Ethylsterone. Now, the next one we are now saying is that, if you recall, we said this is position number 4 and 5. There's a double bond. Now, anything that makes this double bond to shift from, this is, you call it delta 4, because the double bond is at position number 4, starting position number. Anything that makes this bond to shift from number 4 to number 5, for instance, if this double bond is no longer here, but it's not here, it destroys the word progestational activity. So those are some of the things. Now, the conversion of 4-in-3 own structure to allylic alcohol retain full potency. Hence, the necessity of having 3 keto group does not appear as specific for biological activity. Now, what do we mean there? What we are saying is, as this group is here, if you don't even have a double bond O here, if what you have is, let's say, a situation where you have, let me just delete one bond from here. Let's say you have something like this. This, the allylic we are talking about. So if instead of you having this double bond O, what you have is this structure here, OH, it does not have anything to do with the what? The performance. So having this ketone group here has nothing to do with the performance. It can either be a ketone group or what? An allylic group or an allylic alcohol. Allylic alcohol means what? OH. So what they are just saying in essence is, you see that you have a ketone group here or you have what? An OH. Change of ketone and OH will not affect the what? Activity. Do you get it now? The same way they say, you see that you have a beta methyl ketone here or what? An OH. Is that okay? So that's the explanation to that. Now, the next one is removal of CH3 group from carbon 19 gives norethiosterone, which has 5 times more progestational activity. Now, if you look at this very well, told you that most times what you look out for, it's not the normal structure. The normal structure will remain intact. But you see all the substituents here, they can actually what? Change. Things can be added, things can be removed. So what we are saying is this ethisterone. Let me draw the structure of ethisterone. Ethisterone is C double bond O. Alright? This is ethisterone. Now what you are saying is, if you remove this double bond, this bond that is at this position number 19, this number 19, Abi, if you remove this bond that is here, it's no longer ethisterone, but rather it's now what? Norethiosterone. So whenever you remove a group, you use nor also. Whenever you remove a CH2 group, you use nor. Remember that we use nor when the ring did what? Shrink or the size reduction. Why is the size reduction? It changed from 6 carbon to what? 5 carbon. That means a carbon group is lost. Same thing applicable here. So whenever you lost a carbon group also, you use nor. So you see, if you know the structure of only one of the compound like progesterone, you'll be able to draw ethisterone, be able to draw what? Norethiosterone. Every other group surrounding it, you should be able to what? To draw. Like me knowing that testosterone is this structure, I can just add methyl group to it and change it to what? Methyl testosterone. And then it continues like that. Is that okay? So that is that. And one of the structural activity relationship. Now, the activity of non-ethisterone may be increased by substituting chlorine at position 21 or by adding methyl group at carbon 18, which is non-gestrel. So, we can add, which of the carbon do you think is 21? If you look at this very well now, which of the carbon do you think is 21? Now, generally, each of these carbons you have here are, this carbon here, if I want to count, normal ring is 17, right? Here is what? 19. Here is what? 20. Here is what? 21. So if I should put a chlorine here, it increases the what? Activity. Is that okay? If I should put chlorine here, it increases the activity. Now, in the same vein, if at position number 18, if I add a methyl group, think that is what they say, by adding methyl group at position number 18, it gives me non-gestrel, which of course the level form gave us what? Level negestrel. Are you getting it now? Position number 18, what position do you think 18 is? This is 18th position here. So at this 18th position, if you add another group, that is become what? C2H5, become what? Non-gestrel, like level negestrel. Are you getting? If you browse the structure of level negestrel, you are going to see it's going to give us something like C2H5 at this position here. Is that fine? So that is the structural activity relationship. Now, acetylation of 17 hydroxy group of notidrone, this is anything as norethiosterone, result in a product with longer duration of action. What we are saying is this hydroxy group, if you acetylate it, that means you put acetic acid with it, you're going to give the ester. Are you getting it? You give a product with a longer duration of what? Action. So if you put an ester group here, it gives a product with a longer duration of action. So that is everything about the structural activity relationship for progestin. Now, how would you increase the anabolic effect of androgens using a synthetic scheme? Now, how do you increase anabolic effect of androgens? Now, the androgens, they have the androsten side chain, right? Or basic nucleus. That is where you still have the testosterone and the rest, the steroids. Now, what you actually do to increase the anabolic effect of androgens is, what you do in that case is very easy. Synthetic modification at carbon-19 steroid have resulted in the enhancement of anabolic activity. Now, introduction of 17 archive functionality. So at position number 17, if you put an archive group, a removal of carbon-19 methyl group, example, that is when you remove carbon-19, becomes what? 19-nor. Are you getting it? So if you have something like testosterone, for instance, what was the structure of testosterone we said we should draw? We said testosterone is something like this. I don't want this anymore. So we say testosterone is something like this. It has 19 carbons. So it's an androsten. Go east, and we said earlier that the structure. So you have double bond O, something like this, here. Now, what we are saying is that by introducing at position number 17 an archive group like methyl testosterone, are you getting it? You will actually increase the what? Anabolic effect. Also, removal of carbon-19 methyl group. So this is carbon-18 methyl group. This group here is what? Carbon-19. So this is the normal structure of testosterone. Is that okay? If I remove this group from here, I no longer call it testosterone. I will now call it what? 19-nor testosterone. Is that okay? 19-nor testosterone. Or you can add heterocyclic fused ring at position number 1 and 2. Where is 1 and 2? 1 and 2 is somewhere here. 1 and 2. So if you add an heterocyclic fused ring like thiazo ring, it form compounds like tanazole and danazole, and it also increase the anabolic activity. So I may add a heterocyclic ring at this position. Like if you have something like this, an heterocyclic ring attached, may decide to just say, okay, let me add nitrogen here. This is an example of what? An heterocyclic ring. So if you add a heterocyclic ring at position number 1 and 2, you are also increasing the what? The anabolic activity. So what are the 3 things we are looking at if you want to increase anabolic activity? Very easy. 1, put an archive group at position number what? 17. And it must be what? Alpha. 2, remove carbon-19. So it's now giving on no testosterone. 3, add fused ring, heterocyclic fused ring to position number 2 and what? 3. Easy. E.g. stanazole and what? Danazole. This increases the anabolic activity. Now next. The next one is outline 5 side effects of androgens in patients taking this agent. You have increased risk of coronary heart disease, stroke, or obstructed blood vessels, increased aggression and antisocial behavior, liver tumor, jaundice, testicular atrophy in male with consequent sterility or decreased sperm count and abnormal motility and morphology, clitoral enlargement, beard growth baldness, deepened voice, and breast diminution in what? In female. Is that okay? So those are some of the side effects associated. Now, how would you distinguish 3 alpha and 3 beta hydroxy steroid? Suggest a ways of using this method in purification of steroidal mixture. We've actually answered this before. We said in order to distinguish between the 3 alpha and 3 beta, what do? You react it with what? Digitonin complex. Digitonin complex. Is that okay? React it with digitonin complex. So third digitosine, digitonin complex. Which of them did you say is soluble in digitonin? Alpha. And then we said that beta is insoluble, right? Beta is what? Insoluble. So this one will form a precipitate with what? Aqueous alcohol. By so doing, you'll be able to what? Separate them. Is that okay? So that is, we've answered this question. Outline 3 methods of assay of steroid and give example of a chemical equation. Now, this question here, I just decided to put it. Steroidal preparation may be grouped analytically into 2. We have the synthetic origin, those of synthetic origin, and those of what? Natural origin. Is that okay? Synthetic origin and what? Natural origin. Outline 3 methods of assay of steroid and give one example of a chemical equation. The 3 methods I'm going to give to you are: 1, you have acidimetry. Just to outline, I state. 3, you have UV spectroscopy. Can use UV spectroscopy. 4, you can use high performance liquid chromatography, HPLC. Is that okay? You can use high performance liquid chromatography, HPLC, for the analysis. Now, the one that we will look at is the acidimetry. Now, in the acidimetry, what actually happens is you react steroid having 17 alpha 18 group, 17 alpha ethyne group, something like this. We said some of them, like etisterone, non-etisterone, they can have this 17 group, this group here. So you react this group with silver nitrate. Now, this is going to give us a situation where this H will come and join with this HNO3, and this silver will come and join here, right? So what you are going to have will be ROC double bond CAG plus HNO3, which is nitric acid. Now, this nitric acid that you got, the what? Here? Yeah. Yeah, it's going to give you a triple bond. It's going to give you a triple bond. Now, the nitric acid form is titrated with, nitric acid is an acid. This acid here will be titrated with sodium hydroxide. Is that okay? When acid and base react, they will form what? Salt and water. And then you can determine the endpoint potentiometrically. You know potentiometry now. Potentiometrically. Are you getting it now? Now, examples of compounds that can be assayed using this method. I told you that there are compounds that have what? C, triple bond. What are some of the examples of those compounds that we've listed before? Etisterone, right? Then what other example? No-etisterone. No-etisterone. So we have etisterone and then we have what? No-etisterone. Is that okay? So that is that for this question. Discuss why steroidal drug modification is important in the pharmaceutical industry, pharmacists, and patients. Now, increased biological activity. That's one of the reasons. Now, another reason is increased oral activity and duration of action. Effect a separation of biological action. 2 drugs that are actually supposed to work similarly. When you modify them, one will be working in a different way. Are you getting it now? That's what there's effect a separation of biological action. Then obtain better solubility what? Property. Is that okay? So that is the reason why you actually modify drugs. This is something that you can use your brain for. First, increase biological activity. increase oral activity and duration of action, increase a separation of biological action, obtain a better solubility property. You can also say enhance pharmacokinetic parameters, the half-life. So that is that. Now, next, outline 2 therapeutic uses of mifepristone. Mifepristone is used as a contraceptive. It is also used as an emergency contraceptive. It's also used as an agent to induce labor. Now, I don't know if I should put this termination of pregnancy as a therapeutic use, because it looks like not a therapeutic use. And then we have treatment of what? Breast cancer. You use this compound to actually treat breast cancer. Alright? Now next. What is the role of phosphodiesterase enzyme in male sexual function? Now the phosphodiesterase enzyme, what it does is, now there is nitric acid. Everyone know what nitric acid is. Well, nitric acid is what? It relaxes the peripheral muscles, like those of the blood vessels, endothelial peripheral muscles, so that blood can what? To flow. So when the penis, when the penis is stimulated, it must be stimulated first. There will be what? Erection. Now what happens is that stimulation of the penis leads to the release of what? Nitric oxide. Are you getting it now? And nitric oxide will actually react to form what we call cyclic GMP. Cyclic GMP means what? Cyclic guanosine monophosphate. Is that okay? Now this cyclic GMP, the cyclic GMP will further go into various reactions, and at the end of the day there will be what? More release of NO for the penis to get more aroused and then sustain its erection. Now this cyclic GMP here play a very important role in the sexual function, and there is this enzyme, this phosphodiesterase enzyme is actually can break down this cyclic GMP. Are you getting it now? You can easily break down this cyclic GMP. So what we do is, when this phosphodiesterase enzyme break down this cyclic GMP, nitric oxide won't be produced. Nitric oxide not produced, smooth muscle realization will not what? Take place. I mean, realization will not take place, or let's say dilatation, not realization, dilatation. Those arteries and blood vessels will not dilate, and then at the end of the day, the person will be having weak what? Erection. But if we have drugs that can actually fight against this phosphodiesterase enzyme that break down cyclic what? GMP, what are we going to do? If we have drugs that can fight against this, it means that cyclic GMP will not be much in circulation. And you know, the more the cyclic GMP, what happens? More NO, more dilatation, more blood flow to the penis, more blood flow to the penis, more what? Erection, stronger erection. Is that okay? Now, list 3 examples of drugs that could exhibit this enzyme. It's supposed to be inhibit. List 3 examples of drugs that can inhibit this enzyme. The drugs are, you have sildenafil, Are you getting it? We also have, okay, the sildenafil is usually in the citrate form, so we have sildenafil citrate. We also have the other one, which is tadalafil. And then we also have vardenafil. Now this sildenafil citrate is what you know as what? Viagra. Are you getting it now? It's what is known as Viagra. Now, outline the advantages in terms of pharmacokinetic parameters. Now, if you look at the pharmacokinetic parameters, you agree with me that tadalafil have a or is it tadalafil or tadalafil have a half-life of 17.5 hours and reaches plasma concentration within 30 minutes to what? To 6 hours. So it has a median distance of about 2 hours. Is that okay? And then vardenafil actually have half-life of about 4 to 5 hours. All these things, they are what? The pharmacokinetic parameters that we actually stated. Now, if you check your book, you are going to see the next ones. I think that is all. That is all for this session. We'll see you in the next one. Bye-bye.